Okay, so announcements first. We have another lab, another homework posted. The homework I posted, I think Friday. Is that right? And it's been up for a while. That's due Friday, this coming Friday. That has an extra problem for the 567 students. This is, I guess, the first time that's happened. So the last problem is just for the 567 students. The first N-1 problems are for everyone. Lab 2 is up. That required a slight modification to the COM cloud. So of the two channels, audio 0, audio 1, on audio 1, we pulled out the filter. Okay, so it's got the headphone amp driving the line in directly, and that's useful for Lab 2. I think Lab 2 asks you to look at the reconstruction pulse that's used. And so to measure that, you need a way of kind of measuring, a simple pulse sent by the transmitter without it being altered by the filter. So anyway, that filter's been removed on audio 1. That's just for this lab. After this lab's done, we'll put it back, and then that will be that. So that's homework 2, lab 2. Just a reminder that if you want to submit anything late, you don't have to get permission from me. You don't have to inform me. You just put it late, and the grader will mark it late. There's some language in there in the policy sheet about getting permission from me that's only for labs 4 and 5. Okay, so nominally there's no lates allowed in labs 4 and 5. You'll have many weeks to do them. Okay, and we're kind of on a tight grading deadline for both of them. So no lates are allowed for lab 4 and 5 in the absence of extenuating circumstances. For everything else, you can use a late, and if you want to use a late, you don't have to get permission from me or Umair or tell us. You just do it, and the grader will mark it late when she empties the Dropbox at 5 p.m. on Monday. I will post another chapter 3, hopefully today. Chapter 3 is the stuff we're covering now, the linear algebra stuff, linear signal system stuff, and that's that. Any questions? Yeah?
Maybe a dumb question. Why is W equal W Hermitian?
Oh, you have a question about the material.
Sure.
Yeah, I'll stop. Oh, sorry, that should be transposed. Yeah, should be transposed. Sorry. Okay, yeah, let's go through. Okay, any questions about anything else? Okay, so today I'd like to do signals and systems background. As I said, the signals and systems background takes a lot less time than the probability background. We have like maybe about two plus lectures total of signals and systems stuff. So we should be done this week for sure. And then next week we start talking about how to model the COM cloud channel and then how to design communication systems for it and so on. So I said for both probability background and signals and systems background, I wasn't going to do a full-on review. I just zero in on the parts that we would use a lot and that might not have been emphasized in your prior class. So for probability, that was random vectors and it was Bayesian inference, Bayesian detection in particular. For signals and systems, it's what I call finite length effects. Okay, so in signal and systems classes, you typically focus on the kind of doubly infinite signals over the whole real line or all the integers. The math works out very cleanly that way, but we're interested in finite length versions of that. Like I create a wave file, a vector of samples, I send it through COM cloud, I get another wave file out, it's another vector of samples. I want to understand the input-output relation between those two vectors. Okay, so the time horizon is finite, right? I don't have time horizons over like all the integers, right? I have 100 time steps, 1,000 time steps total, okay? So edge effects arise when you look at finite time horizons. And we want to understand how the signal system story, transforms, convolution and stuff carries over to that finite length case. We understand the edge effects in particular and how to deal with them. And I mentioned OFDM, like the really clever idea behind OFDM, you think of it just a way of dealing with the edge effects. Okay, so if you don't understand the edge effects, then OFDM makes no sense. Okay, so I'm just going to cover the finite length version of the signal system story. I'll do it using a linear algebra language. So first is like a bunch of notations, a bunch of definitions. So we'll write Hermitian, superscript H, to be the conjugate transpose or the transpose conjugate, same thing. For complex vectors, the inner product is x Hermitian y as opposed to x transpose y. The norm of a complex vector is square root of the inner product with itself. And you can check this as a non-negative quantity, so that's good. Orthogonal if the inner product is 0, that's natural. For a given matrix M, you define Hermitian as with vectors to be conjugate transpose or transpose conjugate, same thing. All right, and we'll say M is unitary if its inverse is its Hermitian. So if M Hermitian M equals identity, or equivalently M Hermitian equals identity. Okay, so unitary, if you want to relate it to what we know, unitary is like the complex version of orthogonal. Okay, an orthogonal matrix, there's a real matrix whose inverse was its transpose. Unitary is a complex matrix whose inverse is its Hermitian. Okay? Okay, and then we have like phasor vectors coming up a lot. Okay, so I just invented some specialized notation for this. So E sub f is just this normalized phasor. So it's just a phasor at frequency f from time 0 up to time n-1 in discrete time. Okay, this is just like a pound define, like it's just notation that arises a lot, so we just give this a special symbol. Okay, excuse me. So let's talk about transforms first. Okay, so we'll express the DFT and the IDFT as a matrix multiplication, defined as follows. So I'll define the IDFT matrix as just this vector, this matrix comprised of phasors at these different frequencies. So if we just plug in this definition here, okay, it expands out like this. You just have all these phasors at different frequencies and different times. And we noted last time the KL entry of this matrix is e to the j 2 pi k times L over n. Okay, so the matrix will be symmetric, right? In that you swap k and L, you get the same thing. Okay, so W equals W transpose. So I had this wrong when I first wrote it up on the board. It's not Hermitian here, transpose. Okay, so the IDFT matrix is symmetric, but does not equal its own Hermitian. And we define the DFT matrix as opposed to the IDFT matrix, okay, as W Hermitian. Okay. So all this is just like definitions up to this point. We haven't really done anything. Any questions on the definitions? Okay. So we're going to define the discrete Fourier transform in terms of this matrix. So we'll say the inverse discrete Fourier transform, or IDFT, of x. Okay, we just define it to be W x. Like that. Okay, so we're going to define the inverse DFT in this case. I guess I should underline this. The inverse. You're just going to define the inverse DFT through this matrix multiplication. Okay, so for our purposes, that is the definition of the inverse DFT right there. All right, what are we going to call the transformed version of x? So we have a collision of notation here, actually. Okay, so in probability classes, you typically use uppercase to denote random and lowercase to denote a realization of that random quantity, right? Like that, right? On the other hand, in signals and systems classes, you often use uppercase to mean the frequency domain version of this, right? I mean, there are other notational conventions, but that's a common one, okay? It's probably the most common one I've seen, at least in engineering texts. Okay, we can't do both, right? These are in conflict. So, I mean, when you do just probability, that's great. When you do just signal systems, that's great. Okay, in this class, we've got random stuff and we've got transforms. Okay, so we can't use both of these conventions at once. One of them's got to give, okay? We're going to use the probability convention. So x generally denotes random, lowercase deterministic. The one exception is matrices. Matrices are always uppercase even when they're deterministic. Somehow it seems strange to write a lowercase letter for a matrix. So, we'll always use uppercase letters for matrices, but otherwise uppercase means random. So then how do I indicate, like, what do I call the DFT or the IDFT of okay, actually I did this in kind of the reverse order. Let's do the DFT first, if that's okay. Is that okay? We're going to find the IDFT that way in a moment. Let's do the DFT first, okay? Okay, so then what notation do I use to describe the DFT of x? I can't do capital X, as that would indicate randomness, right? Which is not what I want. So here's what we'll do. So the DFT of x, I'm going to write it as follows. So I'm going to write it as x still, but then the arrow that indicates as a vector, we'll just turn it around like that. Is that okay? I invented this notation myself, and I'm rather proud of it, actually. I think it's kind of clever. Does exactly what we needed to. Okay, so mathematically, this and this are the same type of object. They're both just a complex vector. Okay, so when you're running your compiler in your head, reading all the math, okay, anywhere this object can appear, this one can appear, and vice versa. They're the same type of mathematical object. Okay, so they can always appear in place of each other. They're not equal. Okay, this is not equal to that. Okay, they're related this way. And the reason we turn the arrow the other way around here is just to remind us that this is like the frequency domain version of this. Okay, so from now on, whenever I want you to interpret a vector as a frequency domain version of some signal, we'll turn the arrow to the left that way. Any signal that should be interpreted in the time domain, or that just has no time domain or frequency domain interpretation at all, we'll continue to use the right direction. Okay. Okay, and then the inverse transform just defined using W and with the arrows going the other way around. So definition. The inverse discrete Fourier transform to IDFT of x with the left arrow is x right arrow is W, x left arrow, like that. Okay, so to take the frequency domain version of a vector, you take back to the time domain, you take the inverse DFT, that's defined as just W times the vector, and you get the time domain version. Okay, you can check that this matrix multiplication does the usual DFT, IDFT that you learned in a prior class. For our purposes, we'll just take this to be the definition, but you can check it matches what you know. Okay, so in particular, the two operations are inverses of each other. That's why we call it inverse and indirect transform. Okay, we can show that quite easily given what we've done so far. By showing that, right? So two interpretations of this result. One is a signals and systems interpretation, okay, which is that if I take the, if I take the DFT and then the inverse DFT, I get x back, right? I guess I can write it like that, right? Or equivalently, if you take the inverse DFT, then the DFT, you get x back, right? Okay, so one way of interpreting this result is that these are just, the two transforms are inverses of each other. Another interpretation is that in matrix lingo, W is unitary, right? Its inverse is its Hermitian, right? So two ways of thinking about it, linear algebra way and a signals and systems transform way. Okay, so let's, like I said, this is not hard to prove given what we've shown already. So consider W Hermitian W. Let me expand out what W is in terms of these E's. So you have E0, E1 over N, En minus 1 over N, all Hermitian, right? So that's W Hermitian, transpose conjugate. And then we just have W, right? So E0, E1 over N, up to E n minus 1 over N. So I want to show that's identity. Everybody see why it's identity yet? So if you look at the KL entry of W Hermitian W, it's going to be what? So I mean, you take the kth row here and the elf column here, right? Take the inner product of the two, so you'll get e to the k over n Hermitian, e to the l over n. What can I say about that? So this, I'll tell you the answer. You tell me how we know this is true. How can we conclude that? This equal sign right here? Yeah.
K minus L over.
It's what?
When we multiply it.
Yeah. So I have these phasor vectors. I take, nominally two different frequencies. They might be the same, they might be different. Take the inner product between them. The claim is if it's the same, then you get 1. If it's 0, 0. Sorry?
Because 2 pi, well, e raised to 0 is just 1. That's if k equals L.
K equals L, you get 1. How do I know that? Looking for a meta argument here, yeah.
When you multiply those two, E Hermitian and non-Hermitian, each component will turn into e to the j, 2 pi, and then k minus L over n, which is what I was saying. So when they're equal, you just a bunch of sums of 1, so you get n1 is divided by n.
Yeah.
It's 1 over n, 1 over squared.
Okay.
So that's 1 to 0.
Did you just do all that right now? Okay, that's exactly what I was asking. Yes, that is the last problem on homework 1. Right, to show exactly this. This equal sign was the last problem on homework 1. Okay, that's why it was there. Okay, it was not just busy work. Okay, not just to see how well you remember that stuff, because we use it right here. So yeah, indeed. Okay, so these different phasor vectors at integer frequencies divided by n, they form an orthonormal basis. Okay, so they're orthogonal at different frequencies, and at the same frequency you get 1. Okay, so that shows W. That shows that W Hermitian W is identity. Using linear algebra ideas, you can actually show that one of these implies the other. So that's always true in general. In this particular case, I can just show it from first principles using this fact right here. So there's actually a short proof that W Hermitian is also identity. So let me show you that. So W Hermitian is W transpose star, right? Complex conjugate. Okay, then we said W is equal to W transpose, right? So I can remove that transpose in the one place and put it in the other for free, right? W equals W transpose. Yeah? So now factor a conjugate out like that. Yeah? And then this is W Hermitian W. Whole thing conjugate, that's identity conjugate by what we just showed, which is identity. That's that. Okay, so you can actually get the flipped version as well in this particular case. Okay, so that's the Fourier transform in matrix form. Let's talk about convolution. In particular, let's talk about circular convolution. Okay, so first of all, just recall the definition. So given two vectors, say x and c, we'll define the circular convolution as follows. So the kth entry of y, there's going to be sum L equals 0 to L minus 1 Let's do CL x k minus L mod n. So here k is in the same range, 0 to n minus 1. Okay, and you can show this is C circular convolution X, so it's commutative. Okay, I won't show that. You've presumably seen that in a prior class. Okay, so that's circular convolution. I'm going to put this in a matrix form now. Okay, so the DFT we write as a matrix multiplication. I'm going to write circular convolution also as a matrix multiplication. Okay, and there's a reason for doing this. It's not just like an addiction to linear algebra. Okay, so the linear algebra approach will allow us to solve the communication problem a lot more readily than if you just try to do it with signals and systems without matrices. Okay. So circular convolution amounts to multiplying by a matrix with a very certain structure to it. And that structure is called circulant. Okay, so it's circulant if every column can be written as a circular rotation of the column before it. So you have the leftmost column that. Okay, and then every subsequent column you just rotate this downward by 1 with a wraparound. Okay, so the next column will have C0 down 1 on the diagonal, C1 down 1. The last entry will be Cn minus 2, and Cn minus 1 will rotate around to the top. Okay, next column, C0 again on the diagonal. C0 is on the diagonal all the way through. Ahead of it, you have Cn minus 1, Cn minus 2. And the last entry will be Cn minus 3. Okay, and keep going. So rotate n minus 1 times, so you have a square matrix, an n by n matrix. In the last column, C0 will be down at the bottom. So you have C0 in the bottom right corner. Okay, and then C1 is already going to wrap around. That's going to be here. C2, C3, etc. Like that. So C is overloaded here. The letter C is overloaded, right? There's like two C's. There's C, I guess a capital C, the matrix, and then there's a little c, the vector. Little c, in a sense, just defines like the leftmost column of this matrix. Okay, and once you know the leftmost column, you know all the other columns after that because you rotate to get all these other ones. Okay. And we'll use the two C's somewhat interchangeably. So, you know, given this little c, right, I can extrapolate the big C, and given the big C, I can pull out the little c, right? So we can call little c the vector associated with big C, and likewise you can call big C is this. Let's call it the circulant matrix. Generated by or induced by C. That, right? Okay, so the claim is that multiplying by the matrix C is just doing a circular convolution with little c. Okay, so the reason we care about these matrices is that I can think about circular convolution as just a matrix multiplication with that. Okay, so if Y is the circulant matrix C times X, then Y you can write as, doesn't matter which order, I guess. You can write as circular convolution between X and C. Multiplying by this matrix is the same thing as doing a circular convolution with the leftmost column. Okay, so to see this, you got to just like picture it really. So I'm just going to add to this picture here rather than drawing the whole matrix again, if that's okay with you. So think about multiplying this by a vector x. So you have x0 here, x1, to xn minus 1. And let's let the result of that product be called y. So I get a y vector over here, right? Yeah? Okay, so how does y relate to x? So take y0 first. Okay, so how does y0 relate to the c's and the x's? So y0 is going to be an inner product like that, right? Okay, so I can think about summing over the x coordinates, right? I'm going down like that. So L goes from 0 to n minus 1, okay? And then when L equals 0, we get 0. When L equals 1, we have n minus 1. When L equals 2, we have n minus 2, and so on. Okay, so I can write that as 0 minus L mod n, right? When L is 0, I get C0. Okay, when L is 1, you have x1, and then you're going to get C minus 1 mod n. Minus 1 mod n is n minus 1. So I'm going to get x1 times Cn minus 1. That's what I want. x1 times Cn minus 1, and so on. You get x2 times Cn minus 2. That's what we've got here, and so on. Yeah? Likewise, if you look at the one entry for y, it's going to be 1 minus L mod n. Right? So x0 gets multiplied by, over here, x0 gets multiplied by c1. When you're looking at this equation here, y1, x0 gets multiplied by c1, x1 gets multiplied by c0, 2 by like minus 1 mod n, and so on. That's exactly what that equation reads. Okay, and in general, yk sum over x, c, k minus L mod n. Does that match what I have there, hopefully? Yeah. Okay, I've got the x and the c flip, but it's commutative, right? So you can swap the role of x and c here. Okay? So we can view circular convolution as just multiplication by this kind of crazy matrix with this circular structure to it. This little vector c, we sometimes call that the impulse response of this matrix. Okay? See why? Why would that be a reasonable thing to do? I mean, it's a definition, right? So I can define it to be whatever I want, but you know, why would it be reasonable to call this little c the impulse response of this system? Yeah.
So if you put in impulse like a 1 and a bunch of zeros,
Yes.
you get the first column, which is C.
Yeah. Exactly. So for that, it's actually, I think, easiest not to get like confused by this theorem. Just stare at the picture here. So suppose my x is just 1, 0, 0, 0, 0, 0. Okay? We'll call that the impulse input. Okay? 1 and a bunch of zeros. So if you multiply that, what do you get? Well, it's going to pick off the first column, right, and then 0 out the rest. So y ends up being the first column, right? It's helpful to kind of visualize this as like, you know, think of it, you're having a bunch of columns here, and then these are the weights on the columns. Okay, and when you multiply it, you take this column times that weight, this column times that weight, and you add it up. You know, so just think about this thing coming over and weighting this column, x1 coming over and weighting the second column, and just add it up right to left. Okay. I think when you first do like linear algebra, you view like a multiplication like this. Okay, it's this one times this one plus this one times this one plus this. Okay, that's too slow. All right. Think of it more in terms of like weighting the vectors and adding them up. Yeah. So if you do have an impulse as your input, then this will be the output. So it's natural to call this the impulse response. So let's add that right here. Also, C is impulse response. Okay. So here's the part that I think is most exciting. Okay. So you know from prior classes, right, that DFT will turn circular convolution into multiplication? Yeah? Yeah? Okay. Yeah, so DFT will turn circular convolution into multiplication. Okay, if you translate that into linear algebra terms, like the way we're phrasing it here, okay, it says the DFT matrix will diagonalize any circulant matrix. Okay, so here's the big theorem of this section. If C is any, let me emphasize any. Okay, if C is any circulant matrix, then C can be written as follows. C, I'm going to leave some space here. C can be written as W lambda W Hermitian where W and W Hermitian are the IDFT and DFT matrices, respectively, and where lambda is a diagonal matrix with the DFT of the impulse response on the diagonal. With the square root of n. That. Okay, people understand the statement? Let me go through it slowly. Okay, so take any circulant matrix, any matrix with that like circular structure to it. Any matrix of that form, I claim you can decompose it this way. These outer matrices are fixed. That's the IDFT matrix and the DFT matrix. Okay, to get lambda, you do the following. Take the impulse response of C. That's just the left column, the leftmost column. Okay, take the leftmost column of C. That's a vector. Okay, that's the vector C like that, right? Take its DFT. You get another vector that we call that. That's an n-dimensional vector, right? Put that on the diagonal. Put square root of n in front. That's your lambda. People go with the statement? Okay. So as with our earlier result, there are a couple of ways of interpreting this, like a linear algebra way and a signals and systems way. So in linear algebra terms, it's just an eigenvector eigenvalue decomposition. Like remember with symmetric matrices, we had something very similar. Actually, I guess we did for positive semi-definite matrices. But if K is positive semi-definite, then we said K can be written as U lambda U transpose, where lambda is diagonal and non-negative, meaning non-negative components, and U is orthogonal. Okay, and we said the vectors, the columns of U are basically the eigenvectors of K, and these diagonal entries of lambda are the eigenvalues of K. Okay, so we covered this back when we did random vectors. All right, so let's just pattern match here. Okay, so in both cases we're taking a matrix with a special structure to it, right? Here it's circulant. There it's positive semi-definite. So it's not just an arbitrary matrix. You take a matrix with a certain structure to it. Okay, and there you write it as orthogonal matrix times diagonal times orthogonal matrix transpose. Here it's a unitary matrix, diagonal matrix, unitary matrix, Hermitian, right? Okay, so there's a clear analogy between the two. In fact, the columns of W are the eigenvectors of C, as we'll see in the proof, and then these are the eigenvalues. Okay, so that's one way of viewing this result. It's just like the standard, diagonalization type result that you have in linear algebra. It's in that family. Okay, that's, by the way, the reason we define W as the IDFT matrix as opposed to the DFT matrix. Okay, so if you define W as the DFT matrix rather than the IDFT matrix, right, then like everything I say will all go through. It's just that like this result would have the Hermitian here instead of there, and then it kind of runs counter the convention in linear algebra that writes it that way. So that's why we define W as the IDFT matrix rather than the DFT matrix, which seems more natural a priori. Okay, so that's one way of viewing this result. This is a linear algebra, type diagonalization result. I said the other way of viewing it is in terms of signals and systems. Let me throw that to you, actually. So what's the signals and systems way of interpreting this result? Like if you want to translate this statement into English right here, in terms of signals and systems, what would the English translation be? If I do this, I left some space here for a reason. Think about multiplying both sides on the right by x. If the matrices are the same, then certainly for any x, this would be equal to this, right? You see it now? Let's do one side at a time. Left-hand side, how would you translate the left-hand side into English? It's the circular convolution between x and the impulse response, right? What's the right-hand side in English? Yeah. Okay, so the content of this theorem is if you want to take x and do a circular convolution, that's equivalent to taking the same x, take its DFT, multiply in the frequency domain by the DFT of the impulse response of your system, and then take inverse DFT to get back, right? So what this is saying is that circular convolution becomes pointwise multiplication in the frequency domain. Okay, so two ways of thinking about it, just a linear algebra form and a signals and systems form. Okay. Whoops. I'm not on this board, am I? I'm over here. Sorry. I usually prove this. It's a little bit of a climb. It's not too bad. but it's a little bit of an intellectual climb. But this is a really important result for us. Okay, this is probably the single most important result in this class, actually. I mean, we'll have other results that kind of build on it, but if I had to pick one, I'd say this is it. So given how important this is for us, I think it's important to make sure we're all completely convinced of the validity of this. So I will prove it for you. Maybe I should repair the damage I did here. Like that. Okay. So the main step in this is to show that the complex exponentials are eigenvectors of C if C is circulant. Okay, so so for now, just consider the following equation. So let's fix some frequency k, or k over n. Okay, and just imagine taking this phasor and passing it through your system. You get something. Let's call y the something. Okay, this is like y is defined to be this. Okay, so take a phasor, pass it through your system, let y be the output. All right, what can we say about y? So if you look at the mth component of y, I mean, y in general is a circular convolution between the impulse response and this phasor, right? So let's write out the circular convolution and plug in for our phasor. Like that. Right? Okay, so we showed that multiplying by a circular matrix is the same thing as circular convolution with its impulse response. So I'm using that fact. Basically just that fact to go from here to here. I'm also using the definition of E. The E vector. E, this is a phasor vector. It's like that. Okay? Now, tell me about this mod n here. What's it doing? If anything? Do I need it? It swings back around, yes. That's what it's doing nominally, but the phasor also swings back around. Right? And if you had a multiple of n to this, imagine that weren't here. If you had a multiple of n to this, some integer times n, that extra term is going to cancel the n here, and you're just going to get 2 pi, e to the j 2 pi integer. Right? So I've got kind of a redundant periodicity here. The phasor is already redundant, or already periodic, and I've got a mod n thrown into boot. I don't need both. It's not doing anything. Yeah?
Why is the sum to m?
I'm sorry. Yeah. This would be n minus 1. Yeah. Good. Okay, now that I've lost the mod n, I can split this up between m and l. So we're going to have ym is e to the minus j 2 pi, no, let's do e to the j 2 pi k over n times m. So I'm going to pull the m, e to the j 2 pi k over n, m out. And then we'll also have 1 over square root of n there. And then sum l equals 0 to n minus 1, c l e to the minus j 2 pi, what's left here, k over n, l, right? Okay, all you do is split the phasor up. You got the m, you got the l. Okay, the m part we're going to move in front of the summation, the l part we leave there. Okay? Now, tell me about this sum right here. How do we represent that in our notation? Yeah. It's that right? E?
Oh, it's a summation.
Yeah, summation, yeah. I guess I'm cheating a little bit in that we, yeah, sorry.
Is it the W matrix?
Yeah,
Okay.
yeah.
Entry.
We're basically multiplying by that. So which entry?
L.
Well, L is a dummy variable here. Yeah, I'm cheating a little bit in that we define the DFT through a matrix multiplication, but put that aside. Just think about the DFT the way you learned it in your earlier class. In words, what is this?
The inverse UT matrix.
This is just the DFT, actually. It's not the inverse. This is just the DFT. Like, this is, I think, where like, you know, I end up making things more complicated than they really are, right? I mean, if I just said, okay, I have this like finite duration signal C. I want to take the DFT of it. What's the DFT? I think you would all go and write down exactly that, right? Or maybe you'd look up, you'd remind yourself what the definition of the DFT is from your earlier class, and then you go write down exactly that. Okay, that is the DFT of C evaluated at frequency K. All right, and we have notation for that. That's that, right? It's the DFT of C, the DFT of C evaluated at frequency K. Okay, so Ym equals DFT evaluated at frequency K. I'm going to throw in an extra square root of n here. So I can divide by square root of n. So what we get is that y at component m is just DFT of C at frequency K times square root of n. And this is then E F evaluated at m. Okay, and that's true for all m. So if all the components are equal, then the vectors are equal. We get C. Sorry, F is K over N. Like that. Okay, so I'm saying here, to go to the last step, I'm just saying, you know, I have a vector on the left-hand side, a vector on the right-hand side. Okay, they're equal in every component, so we can just say this vector, dropping the evaluation at m, is equal to this vector here evaluated at m. Okay, so y was defined to be this matrix multiplication right here, right? That's what we started with. Y is defined like this. So end to end, we have C times the phasor at frequency k over n is this scalar times the same phasor. That's true for all k. I like to translate stuff into English. I find it a lot more memorable if you translate it into English instead of just, you know, trying to just parse it symbol by symbol. So what have we shown here? In like linear algebraic English, how would you translate that into English? We've shown something rather significant here, actually. There's just a lot of symbols to parse. So I have this matrix. I have a certain vector. I multiply the matrix by the vector. I get the same vector back with a scaling, right? In words, yes.
Yeah, then eigenvector.
Yes, we have, so we conclude by the definition of eigenvector and eigenvalue, right? This must be an eigenvector of that, and then this is the corresponding eigenvalue. Is an eigenvector of C with eigenvalue that DFT business, CK square root of n. Okay, and there's one remarkable thing about this is that, normally when you take a matrix and you go to find its eigenvalues, like the eigenvectors depend on the matrix usually, right? You go to solve the eigenvalue equation. Suppose you know the eigenvalues, you go to compute the eigenvectors just solving a linear system, right? The vector you got will generally depend on the matrix, okay? So here, if the matrix is circulant, it doesn't matter what circulant matrix you've got, okay? This is always an eigenvector by virtue of it being circulant. Okay, so once you know a matrix is circulant, you'd have a bunch of eigenvalues. They're complex, okay, but you have a bunch of eigenvectors that you can just write down. And they don't depend on the particular circulant matrix, only that it's circulant in general. Okay, so that's most of the work right there. So let me show you how we finish this off now. Okay, so now consider this matrix product, C times W. So W is just these phasors lined up. Okay, I multiply C through. Okay, I'm going to invoke the eigenvector-eigenvalue equation right now. So we know what C times the phasor equals. It's the phasor again with this eigenvalue thrown in. Okay, so CE0 is going to be, let's move the square root of n out front. CE0 is going to be C, the DFT of the impulse response at 0 times E0. Okay, so I've just invoked that eigenvector-eigenvalue equation. I've invoked that for k equals 0, I guess, to get this, go from here to here. Then invoke it for k equals 1. You'll get C1 E1 over n, C2 oops, my arrows are all mixed up, E2 over n, C n minus 1 E n minus 1 over n. Okay, so that eigenvector-eigenvalue equation, you apply that n times here, once for each column. So this one gives you this one gives you this one, so on. All right, and all that's left is to rearrange. So this, I want to write that as a matrix product. So to write this as a matrix product, I guess we want E0, E1 over n, E2 over n through En minus 1 over n. And then a diagonal matrix with C0, C1, etc. on the diagonals. Okay, so I think it's easier to go from this to this rather than the other way around. So just stare at this thing and just convince yourself that, like, okay, this is going to give me a matrix. These are both matrices, right? I mean, because they have a set of vectors here. So these are two equal sized matrices. Okay, sorry?
Should be square root of n.
Square root of n, yes, good. It's the third time this lecture I've missed something kind of important. Square root of n. Okay, so the first column of the product is going to be C0 times this vector and then 0, 0, 0, 0, 0, 0, right? Okay, so the first column will then be square root of n, C0, E0. That's what we have here, right? Make sure I got my arrows going the right way. So the phasors are time domain. Here I've got the in the DFT domain, time domain for the E's. I think we're good. Kind of paranoid now about getting stuff wrong. Okay, so this is W times what we were calling lambda. Okay, lambda was exactly this matrix here with square root of n times. Okay, so bottom line, let's finish it right here. Okay, so bottom line, you get C, so end to end, we have CW, right, equals W lambda, right? What's the last step? W Hermitian, yep, exactly. So C W Hermitian equals W lambda W Hermitian. And this is the DFT IDFT. That's it. So the key step is really to show that the phasors are the eigenvectors. And once you have that, then it's just sort of arranging things the right way. Okay. I think it's a very nice story. Okay, so the DFT you can view as a matrix multiplication. It's a unitary matrix multiplication. IDFT is like the inverse unitary matrix. Circular convolution you can write as multiplication by a circulant matrix. Any circulant matrix is diagonalized by the DFT. That's like the linear algebra expression of the usual fact that the DFT turns circular convolution into multiplication. So this is all pretty cool. It also, at first blush, to me, seems rather useless. Okay, it's a pretty story. Okay, but there's like one major hitch, okay, in this, which is that it all talks about circular convolution. Right? Circular convolution is sort of like the key player in here, or maybe circular convolution plus the DFT are the two key players. Circular convolution is not a naturally occurring operation. Okay? Mathematically, you can define it, and it has all kinds of beautiful properties. Okay, but there aren't really systems out in the world that perform circular convolution, at least naturally occurring ones. Okay? There are all kinds of systems that perform regular convolution. Any system that can be viewed as like linear time invariant, you can view it as just like running a convolution constantly. Okay, so every amplifier, every control system, every rocket, they're all just like running a regular convolution, right? None of them are doing circular convolution. The COM cloud, we'll model the COM cloud next week. It's reasonable to model it as a discrete time LTI system if you ignore the noise. As such, it does regular convolution, okay? And the name of the game here is design communication systems for that channel, right? That does regular convolution. All of this talks about circular convolution, right? This does not seem useful at all. That's what we're trying to do, right? So it seems like kind of a cute mathematical story that's not really very useful in practice. Am I right? Okay. So, but there's a reason I tell you this. I mean, if it was really not that useful, we wouldn't be going through it, okay? So it turns out it can be used, but you have to kind of like paper over the difference between regular convolution and circular convolution. Okay, you got to find a way to kind of bridge that gap. Okay, because the real system, COM cloud in our case, is doing regular convolution. Our theory handles circular convolution. Okay, so we got to find a way to bridge that gap. And that's what we'll do actually. So rather than trying to like handle regular convolution directly in this story, okay, we're just going to try to fudge the difference between regular convolution and circular convolution. Okay. So I'll show you how to do that. There are like many ways of doing it. I'll show you a few. including one that'll be really critical for us as the semester wears on. So to start, I think we should put regular convolution in this language. Okay, so if circular convolution is multiplication by a circulant matrix, regular convolution is multiplication by what? Okay, let's answer that question first. Then we'll see what kind of matrices we have to work with, and then how to bridge the gap between them. Okay, people with me? All right. So this is regular convolution now as a matrix operation. Okay, so when you think about regular convolution, you probably think about like doubly infinite signals over the whole real line or all the integers or whatnot. I want to do a finite length version of it. Since that's what we have in practice, and that's also kind of what, I mean, circular convolution is like by definition, you know, over a finite time horizon. So to compare apples to apples, we got to do a finite length version of regular convolution. So here's a thought experiment I want to consider. So consider suppose we have an input signal x, which is just an n-length vector, the usual thing for us. Okay? And an impulse response, h, which I'm going to index a bit differently from the way we normally index vectors. So h0 will be in the middle. You have h minus 1 up to, okay, I need more space, up to h minus n minus. And then h1 up to hn plus. Like that. Okay, so think of these two numbers here. These are integers, n minus, n plus. They describe like the duration of the impulse response in negative time and in positive time. Okay? Okay, now I want to convolve the two. Okay, but what does it mean to convolve, do a regular convolution of a vector and a vector? Like, I mean, it doesn't compute. That's a syntax error, right? And we know how to do regular convolution of signals like over the entire set of integers, like over all time. Okay, but it's not really defined this convolved with this. Okay, but you can get infinite duration signals by just zero padding. So zero pad x to form the discrete time signal x without the arrow, so no vector. I'll write it like that. Okay, so imagine forming like a discrete time signal over all the integers over 0 to n. These are the values right here. Outside of between 0 and n minus 1, these are the values. Outside of that range, just put zeros. Okay, zero pad. Okay? Likewise here. So I'm going to form a discrete time signal h by just extending this with zeros, top and bottom. So zero pad h. To form a discrete time signal h. That. Okay? Okay, let's convolve these two. Oops, no arrow. Let me write it this way. So we're going to convolve the signals x and h to get y. Okay? So just do regular convolution of this x and this h. And then let the vector y be the y signal that comes out of that, evaluated at time 0 up to time n minus 1. Okay, so there are a lot of steps here, but I'd argue it's a rather natural operation. Okay, so you take x, 0 pad it to form a signal over all time. Take h, 0 pad it to form a signal over all time. Convolve them, you get another signal over all time, and then window it. So just delete all the samples outside of this time horizon. Okay? This is a reasonable way of viewing the way the ComCloud system works, actually. The ComCloud system is a linear time invariant system. It's running a convolution, right? On the other hand, we send a finite length wave file to it, and we get a finite length wave file back, right? So how do I think about how that works? Like convolution is like, over all time, but I'm sending in a finite length signal and getting a finite length signal back, right? So one way of thinking about it is, okay, you have your wave file that you create here, okay? And the channel has its impulse response, okay? And there's like nothing going on before or after your signal. So it ends up being 0 padded. The channel then runs a convolution, okay? And then, the receiver like starts recording at one point and then stops recording at another point. So it starts recording at one time, stops recording at another time. And you don't even learn what happened before it started or after it finished. Okay? Yeah?
Do you always start at index 0 in all cases?
No, I mean, you can index it however you want. I mean, I could define, I'm defining, so y is the regular convolution of these two signals, right? So y is a signal over all time. So I can consider this set of samples. I can consider that set of samples. I can go from, minus 50 to minus 25. Like you can start and stop it wherever you want. Yeah. Okay? So here's the question. What's the relation between x, h, and y? How are these things all interrelated to each other? So first thing to convince yourself is that if you fix h, the x to y relation will be linear, right? Because it's like you have several relations here being composed, right? You have that one, that one, right? I 0 pad, I convolve, and then I window, right? If you fix h, just think about going from x to y. Think of h as being fixed. Okay, then you get y by taking your x vector, 0 padding it, convolving, and then windowing, right? Observe, this is linear. This is linear. It's convolution. This is linear. So the whole thing's linear, right? Any linear map I can view as a matrix multiplication. So it must be possible to write y. Let's do it right here. It must be possible to write y as some big matrix times x. And the only question is, what is the matrix? What do we put in there? All right, well, y the vector at 0 is y the signal at time 0. Just think about the convolution sum now. Y the signal at time 0 is going to be h 0 times x 0. What goes here is going to be the anti-causal part of the impulse response. You have h minus 1, h minus 2, and then you'll have zeros filling it out. The vector y at time 1 is the signal y at time 1. That's related to x through the convolution sum as follows. So the coefficient for x1 to y1 would be h0. Looking forward in time is going to be the anti-causal part of the impulse response. The coefficient that x0 uses to influence y1 is the causal part of the impulse response. That's h1. And so on. Here we'll get h2, h1, h0. Maybe I shouldn't have tried to squeeze that in there. h0, zeros. Last one. y1 depends on, yn minus 1 depends on xn minus 1 through the coefficient h0. Zero vectors. Okay, and the coefficient here is going to be the causal part, h1, h2, so on. I have a bunch of zeros here at the end. So it doesn't line up perfectly, but you get the idea. Okay, so just by studying the convolution sum, you can just read out what all these coefficients have got to be here. Okay? Here's my matrix. Yeah?
So when you zero pad, do you not pad on the other side, like before h of 0? Or
Zero pad. Well, we did zero padding to form our infinite duration signals here. I wouldn't.
so what are the zeros in that matrix?
Oh, okay. So so the dimension of this matrix is n by n,
Oh, it's
right?
just a different dimension.
Yeah, it's just the different dimensions. Yeah. So the h. Maybe I should have said at the beginning. Let's assume that n. Suppose your signals are longer than the. Suppose x is longer in duration than the impulse response. Okay, in which case, eventually you get to h of minus n minus here, and then you're out of samples. So the impulse response has been zero padded. Yeah. Okay. There's the matrix. Regular convolution is multiplication by that matrix. Is it circulant? And why not?
Zeros.
I mean, circulant matrix can have zeros. The all zero matrix is circulant. You can have a lot of zeros, actually. Yeah.
I guess, well, it's just like if you shift it, going to the second column, you shift it down one, so that the first, on the first row, second column, it should be h of n minus, or it should be a 0, I guess.
Yeah. So if it was circulant, then every subsequent row would be the first. Sorry, every subsequent column would be the first column rotated, right? The first column would dictate everything. After that, you would just be rotating this thing around, right? Here's a particular value. That value appears nowhere in here. I have h0, h1, h2. I'll get up to hn plus, and then zeros after that. Okay, the anti-causal part of the impulse response does not appear in this first column at all. It appears here, though. It appears here. Likewise, the last column will have only the anti-causal part. It won't have the causal part in it at all. Okay, so these columns cannot be rotations of each other. So this matrix is not circulant. And that's the problem. Okay? So the theory works beautifully if your system amounts to multiplying by a circulant matrix, and our system does not. Our system multiplies by this matrix. Okay? But just as a teaser for Thursday, I'll point out that this is kind of close to being circulant, right? It took a while to stare at it to see it's not circulant. And in fact, if I just could take the anti-causal part and kind of put it down here, and take the causal part and kind of put it up there, then it would be circulant. So it's not circulant, but it's close. And it's close enough that we can kind of fudge the difference with some tricks. Okay, so Thursday will be about the tricks and how we fudge that difference. And then next week we'll talk about the concloud server and how to model it. All right, see you Thursday.